Next one down.
Let you drive from here.
Okay, perfect. All right, my name is Nathan Raymond. This is the electronic tracking system. And I'm just going to read this stuff at the top. I'm going to kind of walk you through my website, a little bit different than what the other guys are doing. So this project aims to replace the manual tracking system, which is part of a design of a 2x72 industrial grade belt grinder. The machine uses a 2 horsepower, 3-phase TFC 220 volt motor in combination with a BFD, variable frequency drive, to control speed, making the grinder suitable for blacksmithing, for bladesmithing and other blacksmithing operations, which require metal removal. Each belt for the grinder is 2 inches wide by 72 inches long and has quite different tracking characteristics. Belts change in firmness and flexibility over time, stretching throughout use. This equates to tracking needed to be adjusted differently for each belt. And as a belt becomes worn, that belt will track slightly different over time. This electronic tracking system will auto-adjust tracking of a single axis, reducing the need for manual adjustments. The electronic tracking system seeks to solve this issue by self-adjusting one axis of the grinder's tracking system. This project makes use of an analog sensor input in the form of infrared beams reflected off the back of each belt. This is IR sensors. This analog value, 0 to 5 volts, is then sent to an analog to digital converter in the form of an Arduino microcontroller. The Arduino board utilizes a 10-bit A to D converter programmed to make a decision on which direction the tracking axis needs to move. To accomplish this movement, the Arduino is outputting digital control signals to a digital stepper driver. It's a DM542T. This takes the input in the form of pulse and direction inputs. These inputs control the speed of the stepper with a PWM signal at the pulse input and a high to low signal at the direction input. The digital stepper driver is powered by DC's power source and drives a NEMA 17 non-captive stepper motor. The motor, in this case, drives a screw and accomplishes linear movement of the tracking axis with continuous feedback from the IR sensors. The belt position can be tracked automatically by the electronic tracking system, as just described. Okay, so I'm going to start with the electrical design here. Okay, so the Arduino is the brains of the system, and I have designed a PCB, what I'm calling a signal routing board. We're taking power and ground up to the PCB, so it doesn't have to be sent all over the place. Otherwise, I'd be sending power and ground to the driver, and then also to the IR sensor. So this allowed me to combine some of these things. I have pins that are going up to the board, and these pins are, the signals are kind of all being collected and put in one place. So the IR sensors, they take a 5 volt, they need a power and a ground for each one. And then they have an analog response. And so the IR sensor, when it's covered, the voltage will increase. And when there's nothing nothing in front of it, so nothing's being reflected back. The voltage will decrease. The stepper motor is, so the IR sensors are giving me feedback to the Arduino, and then the Arduino is making decision, and sending that decision to the stepper driver. And then that signal is then sent to the stepper motor. I also added a screen at the end, because there's some state machine changes that are going on. And so if I didn't have that screen, it's kind of hard to tell what state you're in, because there's a manual jog and then there's an auto tracking. So I have push buttons which are installed here. And so that signal is used to change the states. And when you go into manual jog, you also have to ignore the sensor input, because if you don't ignore it, then the motor would, you might jog to the side and the motor would, the sensors would tell the motor to put it back in the middle. And that does have applications, because sometimes you don't necessarily want to drive the belt in the middle, depending on what attachment you're using. So this is the PCB design. You see we've got power and ground, the pins for the pulse and direction inputs, the outputs of the sensors, and then the power and grounds for the other requirements. This is, you can see this a little bit more clearly. So power and ground again. This is the Osh Park PCB. I've also got one of the PCBs right here. And this board is mounted in my electrical box. Okay. So I'm going to go back to the main page here, and we can take a look at the mechanical design. So this is the original tracking arm. There's two axes of movement. So this front wheel would cause the tracking wheel to tilt. I guess I'd call that a Y change. And then this wheel would cause the wheel, so the front wheel would cause the Y, and then this wheel would cause an X for the wheel to tilt like that. So with my new design here, I've eliminated this front wheel, and now I've got a stepper motor that's driving the change here. So instead of the wheel on the tracking wheel in the front, now the stepper motor does this change automatically. And we can see here a little bit better the front view. And right here we can see, this was my original idea for where the sensors would go. I actually had to change that because the sensors, when I mounted this on the grinder, they didn't really fit there appropriately. And I have some pictures of that, so we'll be able to see that later on. So that's the 3D CAD for the mechanical design that I started with. Let's see the construction progress here. Actually, look at the electronic parts. So this is, we got the Arduino right there, the digital stepper driver, power supply for the digital stepper driver. I didn't mention this in the last, in the electrical design part, but that stepper driver does need its own power supply, because the Arduino can't really drive the stepper motor. And then we have the IR sensors. These just run off 5 volts. and NEMA 17 stepper motor. And I'll go to the electronic parts. Oh, I mean the mechanical parts. So the grinder that I built that last year, and this is a kit grinder. So you buy flat plates of steel, and then you weld it all together. So the tracking arm is a kit. So I bought that kit and welded it up, and then the auto part is this design. The construction progress. So here is the tube. This is the holes that need to be drilled. Then we can see here I'm getting ready to weld this side arm on. The tracking wheel, I'm getting ready to weld that on. That's a bolt with a hole in it to weld that on. Then you can see I've got the side arm on here, and this is the tracking mechanism. Okay, another view. And here's a test with the stepper motor. And here we can see I built a stand for the arm, so it's just with it mounted on there. I didn't use a zip tie to attach that thing, but
Zip tie engine.
yeah, right, yeah, it's yeah. So yeah, that's when I was at about that stage. Okay, so here we have nothing. Okay. So this is my status reports. I must not have shared this correctly. Let me just see if it opens. I have to sign it. Okay, I must have not shared that correctly. That's okay. So let's talk about the digital code here. So this took a lot of coding to make it work in the Arduino. Here we have, this is a stepper driver code specific to a digital stepper driver. This is a state machine include. The state machines in the Arduino are based off a linked list. It's a data structure in C. We have some specific includes. Add a screen at the very end, so you could see what state you were in, because based on the button pushes, you can change states, whether you want to be in the auto tracking or the manual. So we have the setup for the display, the setup for the stepper. Mode 1 just says you're using a digital stepper, and then 7 and 6 are the pins for the direction and the pulse control. These are my button pins. I'm setting the button state to low. And then this code right here is making decisions about the sensor data that's coming in. The IR sensors, I found that based on ambient light, you might need a different trigger level. So I'll have to adjust that to the environment. I'm working on that to get it so the calibration is less. Right now, to calibrate, you just have to change the number in one place, but I'm trying to get it so it can do it by itself. I'm setting some flags here. I also have a debounce delay for the buttons. Okay, so with Arduino, this is the way that you create state machines. So we start the state machine. we add the 3 states. In the setup here, I start the delay, activate the serial port. I also discovered that you can't use the serial port for debugging and the display at the same time. Because I was doing a lot of debugging with the serial port, sending me data on the variables. As soon as I started using the display, I realized, oh, you can't send data like that through the to both the serial port and the display. So let's go down here. So here I'm reading the analog value. This is the initial levels of the sensors. This is me trying to calibrate them. So over the first 6 seconds, it reads the sensors and then it averages them. So I take a value here, and it'll only do that once. And then this is the debounce code. So then what I'm trying to do is read the sensor minus the initial values. So basically set those values back to 0 and then have them both use the trigger level, because this inside sensor might be 200 and this other one might be 100. So I'm trying to bring them back to the same place with that code. Okay. This is used for the display function. And now we exit that. We have the 3 states here, a menu state, an auto jog state or auto tracking state, and then a manual tracking state. And then this is the number of steps that the motor will move. And you have to add transitions individually. So those are for the states. And then these are the functions for the display. So you have to obviously build a function for each display and then have it switch. And the reason I'm setting all those flags is so the display isn't constantly blinking over and over and over again. If I didn't set those flags earlier, then every time the state machine ran, it would blink this. So you just have a blinking display. Okay, so I'll show you one other thing here. The final product. All right. So here we have the electronics box. You can see the Arduino here, the DC power supply, and the stepper motor driver. Here you can see the display and the PCB all wired up. Another picture of the inside. And then here is the final machine. So we've got the sensors here put in the front. Then we have the stepper here on the side. I was gonna build a bracket for this, but in the end, I was like, I got a hose clamp would hold that on. So that's what I wound up doing. I did have a plan to build a bracket, but it was going to be really thick. And so I decided I would just use the hose clamp to hold it on. And yeah, so that's the overall design there, and I'll have that to show off in the other room. Okay, good thing I loaded 2 of those, huh? All right, so this is the grinder in action here, and I'm just gonna load that, open that, and I'll turn that down a little bit, I guess. This is the original tracking mechanism.
Can't even see it move.
I'm pushing the buttons, right, to make it manually jog. I'm not turning the wheel on the front anymore, so. We'll go back into auto. All right, so this is during my testing. So now it's making its decisions by itself. So the step size of the motor is too big at this point, and the corrections are overshooting the sensors. So the belt is it's taking too long to find center. Manual jog. See the motor. Belt. Saved it. I almost jogged it off the wheel. Now the exit manual jog. Yeah, it crashed the belt. Okay, now it's auto tracking.
That's why I turned it down, isn't
Yeah,
it? You got this comment.
yeah, but well. Okay, so you can see the step size being a little smaller. It's found its center a lot sooner. Belt is running true.
So that handle still allows manual?
That's for the x-axis.
Oh.
So this one's controlling the y-axis. The x doesn't get adjusted nearly as much. Now we're ready to grind away.
It didn't get hot?
It's no, it's holdable, depending on what belt type you're using. The ceramic belts really they don't heat up the material as quickly. So that, I believe that's gonna about do it. I just have some acknowledgements here. Michael Marcel, Barry, thank you. Kevin Orris, Pat helped bounce some ideas off of him. And then my dad helped me weld some of this stuff up. So the mechanical parts, it's hard to really weld and do all this stuff sometimes by yourself. So I did have some help. Any questions?
So where was that shop? Your dad's garage?
That's at home, yeah. Yeah. Yep. Yeah, I built that last year. It's a 2x72. And all welded up and powder coated and nice and pretty. So building one was the only way I could get my hands on one. So.
And your application is, what was your application?
Oh, blacksmithing. I started blacksmithing last year as a hobby. So use it for that. Yeah, metal removal.
Knife making?
Knife making, exactly. Yeah. Yeah. Good. Yeah.
How was your budget?
My budget, if the status report had loaded, you would have seen that. My budget, I used just about all the money. Yeah, it was like $12 left out of like 600 when I did it. So I had to order the stepper motor twice. And I had originally created a system with lower specs. Like the motor was smaller, there was originally gonna be a board that went on top, it was a shield that went on top of the Arduino, and that was gonna drive the motor. And I started thinking about this. When I got the motor, I was like, oh, it's really small. It was NEMA, the next size down, I'm not sure if it's 12 or 11. It was the next size down, and I just decided to beef everything up. So I reordered the motor and the driver. So there's 2 motor orders in there. But yeah, there wasn't too much left. Then I bought the box at the end to contain the electronics. And then the PCB, I also designed the PCB originally. I didn't have that in there. And this was, the price has changed on these. And I didn't realize I had made it this big either. So I got it back and I was like, oh, that's really big. So there could be some money saved with single orders and, you know, a PCB that could have been maybe this big instead of that big, but learn from that, so.
Any other questions? I know, Ian, you originally selected a NEMA 23 motor,
Right,
and we were talking about supply chain issues earlier, and
yes, there was one coming from China. And I didn't realize it was coming from China because the Kevin was ordering everything. And it didn't say on the website that it was coming from China. So he saw that it was coming from China, but I didn't. So there was 2 weeks where we were just waiting for the motor. And I was like, well, send them a message and figure out what's going on. And then he was like, I sent them a message and they canceled the order. So I was like, okay, there's 2 weeks gone. So yeah, definitely had some supply chain issues. So. Okay, perfect.
all right.
All right.
Thank you very much. Well, that concludes the presentations. I want to thank everyone for coming. And look, we finished just in time for pizza delivery, although I don't know where the Zachary's Pizza guy is. But we're going to be setting up the projects in our electrical/projects lab 213. If you want to stick around and see the projects and talk to the owners and the creators and get to know them a little bit better. But I want to thank you folks for coming today. Nice Vermont spring day out there. You're supposed to get in the low 70s. So thank you again, and please enjoy some pizza and talking with the students. Thank you very much. So, Brian, thank you very much for today. And we'll enjoy the rest of the day.
What do you guys do? Engineer, design, manufacture.